Hello students, welcome to the class. So today we will continue with the thermodynamics chapter. We will be covering today section 5.2.2, which is theory part 4. So this is the disclaimer. In our today's class, our objective would be to explain a very important state function. So we have already dealt with U, which is our internal energy. We will talk more about it. And apart from that, we will also look at a new state function, which is enthalpy. And it's very important for you. Now, I will also try to correlate both of them, and the correlation will be between your internal energy and your enthalpy change. Okay. Then if I talk about the specific topics that I am going to cover according to the NCERT, so there will be 5.2.2, which is enthalpy, in which we will also cover the heat capacity, the relationship between the Cp and Cv. So the famous relationship, we will study it, try to derive it also, and in-text question, which is 5.5. Apart from this, we also have a very important topic. I am keeping this as a surprise for you. Now, starting from the first thing, which is enthalpy. It's a very simple and a very useful state function. Okay, so it is simply the sum of internal energy and the product of the pressure and the volume. How we can write it mathematically? So mathematically we can write it as H is equals to U plus PV. Now this is the equation for enthalpy, but we are interested in change of enthalpy. Every state function that you will study, in every state function you will be interested in their change and not in their actual value, because first of all it is impossible to calculate the actual value, and second, the useful part is the change, not your actual value. As I have told you that your enthalpy is a state function. Why it is a state function? Because the things on which your enthalpy depends are internal energy, pressure and volume. So you can see all of these three in the equation, and all of these three are what? They are state function. Therefore, your enthalpy will be also a state function. Okay. Now we will try to derive a useful equation for the change in enthalpy. For that, we will take the original equation of enthalpy, which is H is equals to U plus PV, and we will write it for finite change. So how do we represent change in thermodynamics? We use two things. First is D, small d, and that is used for small amount of change, or you can say infinitesimal change. Okay. And for finite change, what do we use? We use the term delta. So if you just take the change here, so it can be written as delta H is equals to delta U plus delta PV. Now, if I take the pressure constant here, then we can bring out the pressure out of the delta box. Okay. So now the equation becomes delta H is equals to delta U plus P delta V. Now why are we pulling this P apart from the delta? Because pressure is taken as constant. Now what is the reason that we are keeping the pressure constant? Why we are trying to define an equation that is related at constant temperature, constant pressure? So the reason is that most of the chemical reactions that you do in the laboratory, they are done in the atmospheric pressure. Okay, so that is done always in the atmospheric pressure, which is present around the laboratory or in the laboratory. Therefore, the pressure is not changed, or it is constant. Yes, the volume will of course change. If there is a release of gas, that volume will result in an abrupt change, but your pressure, which is around the beaker in which you are doing the reaction, will not change. Therefore, it is a very good idea to keep the pressure constant, and this will also simplify your condition. So this equation is very important, which is delta H is equals to delta U plus P delta V. Now the other form of equation, which is delta H is equals to delta U plus delta PV, which is this equation, right? So this equation, this is also very, very important. Okay. So wherever you see that the pressure and volume both are changing, you can use this equation, and at constant pressure you can use the equation number 5.8. Now, what is the relation of heat with energy? How do we relate both of them? We know that from the first law of thermodynamics, delta U is equals to Q plus W. Okay. Now what will happen at constant pressure? We will take Q as QP. So this is just a notation. Okay. So to represent the heat change at constant pressure, we write Q as QP. Okay. So P is present in the subscript part. Similarly, what is work? What is the formula for work? We have already seen it. It is minus P delta V. Okay. So equation 5.1 can be written as delta U is equals to QP minus P delta V. So we are just substituting the values that we have seen at a constant pressure. Okay. Now you will question that I am keeping the pressure constant, then why are we not taking the work as 0? Because we are not changing the value of pressure. Okay. So the change in the pressure is 0. The actual pressure is something which is not equals to 0 absolutely. Okay. So this should be kept in your mind always. Now, if you consider the above equation for two different states, suppose 2 and 1. So how we will write it? We will write it as U2 minus U1 is equals to QP minus V2 minus V1. Okay. So what we have done? We have just replaced delta U with U2 minus U1 and delta V with V2 minus V1. Rest of this will be same. So U2 minus U1 is equals to QP minus P into V2 minus V1. What will happen on rearranging this equation? We will get our equation as QP is equals to U2 plus PV2 minus U1 is U1 plus PV1. So this is a very simple arithmetical operation. You can try it by yourself. Here will be the first equation, which is U2 minus U1 is equals to QP minus P into V2 minus V1. Just rearrange it and you will get your final equation. Now what we can do with this equation? Is there anything that we have seen similar to this equation? Yes. What is that equation? That equation is of enthalpy. So how can we write it? We know that H is equals to U plus PV. Therefore, your equation 5.6 becomes, your previous equation becomes QP is equals to H2 minus H1. So for the first U plus PV1, we have written it as H2, and for U2 plus PV2, we have written it as H2, which can be written as H2 minus H1, which is delta H. So these are the substitutions that we have done. Okay. H1 is equals to U1 PV1 and H2 is equals to U2 PV2. So there will be no delta here. It will be simply H1 is equals to U1 PP1 and H2 is equals to U2 PV2. So what we can infer from here? We can infer a very important relationship between the heat change and the enthalpy. So we can write that heat change at constant pressure will be equals to the enthalpy change. Okay, so this is very, very important and it is applicable only at constant pressure. So what we can tell from here, a very straightforward point can be directed. If your enthalpy, okay, if your enthalpy is a state function, therefore your heat change at constant pressure, which is QP, will also be a state function because delta H is equals to the QP. Now, what is the significance of this enthalpy? So, two important significance are there. First is, if your delta H is negative, then your reaction is exothermic. What is the meaning of exothermic? It means that heat is evolved during the reaction or it is released during the reaction. We can take an example of it. Suppose we are doing a combustion in a combustion reaction of the hydrocarbon such as methane will give you some amount of heat. So we have represented that heat with a negative sign. Okay, so always for exothermic reaction, you will take a negative sign along with the value. So here it is minus 890.3 kilojoule per mole. Now, how do we write it for the positive? So for the positive case, the delta H is there for a reaction and it is called as endothermic reaction. And simply in this case, the heat is absorbed from the surrounding. Now, what example can we take? We can take the example for decomposition of calcium carbonate, which is decomposing into calcium oxide and carbon dioxide to give us a 178.3 kilojoule of heat for per mole of calcium carbonate. I hope you got the point, which is related to the significance of enthalpy. Now we will try to develop a very important relationship between delta H and delta U. And this is true only for the gaseous reaction. How? Suppose we consider a reaction which is going from A to B. Then we are considering two things here. First is about volume. So the reactant's volume is taken as VA and the product's volume is taken as VB. And the second assumption we are doing is related to the number of moles. So the number of moles of A is represented by Na and the number of moles of B is represented by Nb. Now, if you apply the gaseous law onto this two kind of species, which is reactant and product, you will get two equations. First is PVA is equals to NART. Here remember we are keeping the pressure constant. Okay, so we are taking P for both of the situations of A and B. So for the reactant case, we are writing it as PVA is equals to NART. Temperature will be also constant and R is already a constant. What can be the second situation? It can be PVB, which is volume of the product is equals to NBRT. So these are the application of the gas law onto the reactants and products. If we subtract both of these equations, what we will get? We will get PVB minus PVA is equals to NBRT minus NART. Take the RT common out of it, you will get your NB minus Na multiplied by RT. Now, if you just rearrange this equation further, you can take the pressure also constant out of it. And this will give you your final equation, which is P delta V is equals to delta NGRT. Now, I have used a very special kind of subscript here for the N. Rather than writing it as simple N, I am writing it as Ng. Okay. What is that delta Ng? It is the change in number of gaseous molecules when we are moving from the reactant to product. Okay. So remember, this change in moles or molecules is only related to the gases and not to any other state. Now remember this equation P delta V is equals to delta NGRT. Let us bring back our previous equation. What is that equation? It is delta H is equals to delta U plus P delta V. And in this case, let us substitute the P delta V with delta NGRT. So what we will get as the final equation? So you got your very important equation from here, which is delta H is equals to delta U plus delta NGRT. So if you know the delta H, you can calculate the delta U very easily just by looking at the chemical equation. Now let us consider different cases for this delta Ng. So three different cases are here. First is your delta Ng can be 0. So it will be possible when the number of gaseous molecules are same on the reactant and product side, or there are no gases involved in your reaction, only solids and liquids are involved in the reaction. What is the second case? That we have positive value of delta Ng. So in that case, your delta H will be greater. When we will get the positive value of delta Ng? When the number of gaseous molecule on the product side is greater. Okay. The third case is when your change in number of gaseous molecule is less than 0. And in that case, you have a greater number of product as the gaseous molecule, and delta U will be greater than delta H in that case. Okay, so I hope you got the three situations, and it's very, very important to consider all of these three. You will notice them here and there. Now, if this thing is clear, let us move on to the next topic, which is heat capacity. How can we define it? So just think it visually. What is that visual thinking? It is that temperature which you will need to raise the temperature of any amount of substance, or a given amount of substance, I would say, by a unit degree. Okay, so I'm not specifying the unit right now, and you also need not to do the same, because the change in case of temperature has no effect of unit. It will be same amount of change in terms of Fahrenheit, in terms of Kelvin, in terms of Celsius. Now, again, I am repeating it. What is heat capacity? It is the amount of heat that you will give to a given amount of substance, so that, or a given mass of a substance, so that you can raise its temperature by 1 unit degree. Now, think of a situation. If you are supplying a heat to a very colder body that is present around you. Okay, suppose you are supplying a heat to the ice. In that case, you will see a very drastic change in its temperature as compared to the normal water. If you apply even a simple amount of heat, it will quickly start to melt. Now, what is observed here? That the heat that you need to require to raise the temperature of a given body is lesser for smaller, is greater for smaller temperature. Okay, so by applying a very small amount of heat to a body at a lower temperature, you will be easily able to raise the temperature of the same body. So we can say that your heat supplied to raise the temperature by a delta amount is directly proportional to the temperature change. Okay, and if you remove the proportionality constant, you can write it as C delta T. So Q is equals to C delta T. Now, this heat capacity, or this C that you have seen it right here. So we already know what is C here. It is your heat capacity. So this heat capacity depends on various things. First is your size. So greater is the size, greater amount of heat you will require to supply to the given substance. Second is what? Second is composition. So it is dependent upon the composition of the matter whose temperature you are trying to raise. Third is the nature of the system. And third and fourth is the amount of substance. Okay, so your heat capacity will depend upon these four things. Okay, I hope this is clear to you. So you can say in a very small point that it is dependent upon the substance for which you are trying to raise the temperature. Now let us specify this thing. First is the molar heat capacity. What is molar heat capacity? In the previous case, we are saying that we have to raise the temperature for a given amount of substance. Now we are defining that amount and telling it as the amount of temperature that you will need, or the amount of heat, not the temperature, the amount of heat that you will need to raise the temperature of a given body by 1 unit degree Celsius, whose number of moles is 1. Okay, whose number of moles is 1. Now, how you can relate it with the normal heat capacity? It's very simple. So your molar heat capacity is equals to the heat capacity divided by the total number of moles, C by N. What is the terminologies that are used here? So of course, Cm is the molar heat capacity, C is the heat capacity, we have already dealt with it, and N is the number of moles of substance. Now, let us move on to one next type, which is specific heat capacity, or specific heat capacity represented by Cs. What is Cs here? In this case, it is representing the amount of heat that you will need to raise the temperature of a given body by 1 unit, given that your mass of the substance is 1 gram. Okay, so here you are defining the mass, or it can be 1 kg. So basically you are trying to raise the temperature for 1 unit mass. Okay, that unit can be anything, and the amount of heat that you are giving to it is called as the specific heat capacity. How can we define it? It's very simple. Just relate it with the mass. So Q is equals to Cs m delta T, where m is the mass of the substance, then Cs is the heat capacity, and lastly delta T is the temperature change. So this formula is similar to your molar heat capacity. Okay, we have just rearranged it. How can we say that it is same? So what you will write for Q delta T? So it will be C, and Cs will be equals to C by M. You can just try to rearrange this equation and get the same thing, only here the mass is replacing the number of moles. So you are calculating it for 1 unit mass. In that case, you are calculating it for the 1 mole of substance. Now let us move on to a very important relationship, which is Cp minus Cv is equals to R, and it's a very famous relationship. We will try to define and derive it both. So what's the definition of it? It simply says that the heat capacity at constant volume is termed as Cv. Okay, and the heat capacity at constant pressure is termed as Cp. Next thing what we can write, if you are trying to define the QV here, that is heat change as constant volume. So from the previous definition of the heat capacity, you can write QV is equals to Cv delta T. And you also know it at the same time that QV is equals to delta U. We have already seen it in the previous class. What is the next heat term that you know? So that term is related to constant pressure. Okay, so QP is equals to Cp delta T, and you know it already with the definition right now that we have derived, that QP is delta H. Now using the ideal gas equation, what we can write? Delta H is equals to delta U plus delta PV. We have seen this equation. Or in place of PV, we can write RT. Now your R is again a constant. So by nature it is constant. We will put out this R. Therefore, we will get delta H is equals to delta U plus R delta T. Now we are defining it for 1 mole. Therefore, we are not writing the term N here. If it was there, in that case also it will come out of the delta, because the number of moles is always fixed. Why I am saying it so? Because in the start of the lecture I have told you that we will only deal with those systems which are closed system. There is no change of number of moles or number of substance. Okay. Now let us move further on this derivation. So we know it already that delta H minus delta U is equals to R delta T. Then substituting the delta H and delta U from the previous equations, we can write Cp delta T minus Cv delta T is equals to R delta T. It's very simple. This is directly from our previous equation. Or else we can divide the whole thing by delta T and we will get the Cp minus Cv is equals to R. So this is equation number 5.13, and this is very important relation. Now we will move on to an extra topic that I have told you in the start, and that extra topic is related to gamma. What is gamma? It is the ratio of Cp and Cv. Very simple. The ratio of the specific heats is known as the adiabatic index, and it is given by the value Cp by Cv. It's very simple. Now the important part is related to the calculation of the Cp and Cv for different kind of molecules. If your molecule is monoatomic, your Cv will be 3 by 2R. If it is diatomic, it will be 5 by 2R. If it is triatomic, it will be 7 by 2R. Okay. Then what we have here, it is the Cp value. For monoatomic, it is 5 by 2. For diatomic, 7 by 2. And for the triatomic, it is 9 by 2. Just divide Cp and Cv and you will get the gamma value for the given 3 types of molecules. Okay. Now the greatest gamma value is for the monoatomic, then comes your di, and lastly comes your triatomic. So these are very, very important relations. If questions are asked from here, and this ratio is directly asked in the question for the case of mono, di and tri. Using this relation, we will try to derive a relation between the work done. Okay. Now there is a small twist here. What is that twist? So our normal gaseous equation is written in a very different way for the adiabatic process. How do we write it? So three things are there. So rather than writing it as PV is equals to constant, we write it as PV gamma is equals to constant, where gamma is your same Cp by Cv. Then the next equation is Tv gamma minus 1 is constant, and the last one is Tp1 minus gamma y, gamma is constant. In place of this, you can also write it as P1 V1 gamma is equals to P2 V2 gamma, because both are equals to constant, so we can just equate both situations. Remember, this is only applicable for adiabatic processes. Now, if you want to calculate the work done by the system, it's very simple. You know it very well that work done is equals to negative of the delta U. Okay. If you are changing the internal energy and writing this thing in terms of Cv delta T, whose equation we have seen it just now. So delta U is equals to NCV delta T. We have just seen the equation. If you put this equation in the delta W, what you can write? Delta W is equals to minus Cv delta T. Okay, so we got the equation. Our next task is to define a value for Cv. We already know gamma is equals to Cp by Cv. Then using the relation Cp minus Cv is equals to R, we can write gamma is Cv minus what? Cv minus Cv by Cp by R. Okay. So what we have done? We have simply multiplied the gamma with C, V, and subtracted it with the Cp. So what we got here? Gamma into Cv minus Cv by R. Is it clear? How are we doing it? Okay, just use both of this equation, you will get this. Gamma Cv minus Cv is equals to R. Further, if you divide both sides by gamma minus 1, you will get your Cv is equals to R by gamma minus 1. So what would I have done here? Here I have replaced this Cp with this equation. So according to this equation, Cp can be written as R plus Cv. So I have simply replaced this Cp as R plus Cv and then rearranged it to get this equation. Okay. Now we got the value of Cv. What can we do? We can substitute the value of Cv in the work done. So we got it as R by gamma minus 1. We substitute it here. So what was the previous formula? It was NCV dt. Now R delta T will be equals to P2 V2 minus P1 V1. So we can finally write our equation as P2 V2 minus P1 V1 by gamma minus 1 with a negative sign. So this is the work done. Okay. This is the work done in case of adiabatic process. Okay. So this is very, very important relation. Got it? Now we'll try to do a question. So that question says that if water vapor is assumed to be a perfect gas, the molar enthalpy change for the vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoule per mole. You have to calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius. So, your time to solve this question starts now. So your time is up. Now, in this question, you have to first look what is happening. So just try to write the situation with the help of simple equation. So according to the given question, your enthalpy change for the conversion of 1 mole of water, which is at 1 bar pressure and 100 degrees Celsius, to your vapor is 41 kilojoule per mole. So this is the enthalpy change during the process. Okay, and what is the temperature change? So you are moving by 100 degrees Celsius. Okay, so there is no temperature change. It is all happening at 100 degrees Celsius. So you can write the temperature as 373.15 Kelvin in terms of Kelvin. Then I said, just visualize the same with the help of a reaction. So we are going from H2O liquid to H2O gas. Then what is the number of change in gaseous product minus reactant? It's very simple. There are no reactants which are gaseous on the reactant side. Okay, there is only one gaseous product, which is H2O gas or vapor. So we can write the change in gaseous number of moles will be equals to 1 mole. Now let us put this equation and use it in the relation between delta H and delta U that we already got. If we substitute it in the formula, delta H is equals to delta U plus delta NGRT, then what we will get? Delta U is equals to delta H minus delta NGRT. So I have simplified it further and then substituted the values. The values are given 41 kilojoule per mole and the gas constant is 8.3 joule per mole. Then we have this temperature. What we get as the result? We get it as 37.904 kilojoule per mole. So do not forget to convert this 8.3 joule per mole per Kelvin into kilojoule. Okay, how do we convert it? It's very simple. You just have to multiply this whole thing with 10 to the power minus 3 for the conversion part. Then you will get your right side thing as kilojoule per mole. Got it? Okay. So this was all for today's class. I hope you enjoyed the lecture.